what's that metal, lab? So I have an unknown metal in boiling water here. Right before you guys walked in, I got the mass of this metal. For you virtual folks, I can kind of move my camera. There she is. What is that metal boiling in there? So we don't know what that metal is. This is a lab that you guys would normally do, where I would have 3 or 4 different kinds of metal, and I'd be like, here, pick one. Tell me what it is. And you'd have to go test it, get data, do some calculations, and then tell me what metal you think it is. So this is sometimes applied to analytical chemistry. Sometimes we're like, well, I don't know what metal this is. And they may have to do something along those lines, along these lines. But anyways, so this metal's mass is 57.05. So we're going to go ahead and calculate its heat capacity. And based on our calculations, we'll use the chart below this right here, where it has heat capacity. So it talks to us about aluminum, lead, copper, and maybe iron. Is iron the other one on there? Tin. Tin's the other one on there. So we're going to calculate what this piece of metal's heat capacity is at C. And it will line up like, oh, it must be aluminum, oh, it must be copper, it must be tin, whatever, based on our results. So I'm boiling this puppy. I'm going to go ahead, I'll get my mass, my empty cups. Make sure they're pretty empty. What do I need to press on my scale before I do anything? 0 or tare. Nicely done. Plopping those cups on there. I got a 9.87. There she is. Boom. Alrighty. Now I'm going to get some water, about 100 milliliters. So I'll go ahead and fill this puppy up. Ooh, hello. Wow, that's very close to 100. Mr. Pilcher, you didn't measure that water exactly. That's all right, because I can get its mass exactly. 0, flop. So I'm not going to write this in this chart. I'm going to write this up above. But let's see here. I'm going to go like this. Get that out of the way. So the H2O plus the cup is 107.98. When we subtract the cup itself, which was 9.87, we should be able to know the mass exactly as the H2O. Somebody help me. 98.11. 98.11. That sounds right. And so that is what goes down here for our actual mass. Now let me mention something about your guys' quiz on Friday. On Friday, I won't make you do the whole cups mass thing, that this sort of subtraction up here. I'll just give you the mass of the water straight up. Okay? Make sense? So you don't need to worry about this on Friday, but I do want to make sure you understand how we do get the mass by subtracting the mass of the cup from the mass of the cup in the water, etc. Okay, well, let's go ahead and get the initial temp of that water. Turn this guy on. Stir it up. So the water temperature is dropping here for a second. Now, I'm boiling this piece of metal. It's been boiling for at least 5 minutes now. What's the temperature of boiling water? So what's the temperature of that piece of metal that's been in that 100-degree boiling water for a while? 100 degrees, okay? Good. The initial temp of the water, 22.5. Okay. Now, I'm going to go ahead and I'm going to quickly get this bolt and drop it into my cup of water. Okay, so I'm going to quickly grab this little fella. Let's see. I do. Plop. It's a very, very small string, so that way the mass of the string compared to the rest of the bolt is basically nothing. But that's why I didn't use yarn. Does that kind of make sense? Alright. Okay. Alright, temperature is cooking up a little bit. I'm going to turn this boiling water, there we go, off. So that's a convenient part of boiling water staying at 100 degrees Celsius. If we plop something in there, if it's in there for 5 or 10 minutes, we know it's basically the same temperature the whole time. So I didn't have to measure how long it had been in the water, as long as it had been in the water the whole time. And now we are looking at a cool 26 Okay. On Friday, you will be given this right here in blue. This is all you're going to be given on Friday, and you have to be able to tell me the heat capacity or whatever it is I'm asking you for of the metal. So right now, I'm going to go ahead and I'm going to give you guys several minutes. See if you can figure out what to do with this. A couple of quick questions. Hey, the Q of the metal should be, the energy that the metal loses should be equal to the energy that the metal loses should be equal to the energy that the water gains. Love it, Blaze. And what? Oh man, 4.18 heat capacity of water. Get them cooking. Let's go. So let me walk you guys through this here. Okay. So I'm going to get this nice and organized. I'm going to get really organized. Here's what I kind of like to do on these types of problems. Okay. So I'm going to divide this in two halves where I have stuff about water over here and about the metal over here. I'll even write them in two different colors just to make sure I'm clear. Okay. So Q equals MC delta T. Q equals MC delta T. Okay. So I asked you for the C of metal, the heat capacity of the metal. So like, okay, well, I don't need the water stuff then. I guess I'm just going to go ahead and plug this in. So you're here like, okay, I don't know what the Q of the metal is, so I'll just keep that as a Q. The mass of the metal is 57.05. The C of the metal is what Mr. P asked me for, so I don't know. The delta T of the metal, Oshwak, what would that be? Very close. It's high 70s. 73.5. Did you say 74, right? Yeah. Okay. Yes. So why is that? Well, remember, the metal started at 100 and went down to 26.5. So when I want the Q of the metal, I need the mass of the metal, the C of the metal, and the delta T of the metal from the metal's perspective. Okay? So this is 73.5. Now, this is the problem that a lot of people ran into. They're like, wait, hold on a second. I don't know the Q or the C. What am I supposed to do this problem? I can't figure this out if I have two unknown variables. You're absolutely correct. So what's going to happen is, this Q, the energy that the metal lost, should be equal to what? The energy gained by the water. In other words, this Q and this Q should be equal. So if I can calculate this Q for the water, I should be able to plug that back into the Q for the metal. So, Q for the water. I want the Q of the water. I need to use the mass of the water, the C of the water, the delta T of the water. I hope this is getting annoying, okay? Make sure you use water all the way across for your Q problems. Okay, so, I'm sorry, all the way across when you're talking about the Q of water. So the mass of the water, 98.11. The C of the water is, the C of the water is, the C of the water is, 4.18. Never forget, never forget. And how much did the temperature change? How much did the water temperature change, Cece?
4 degrees.
Yeah, 4 degrees. You're finding the gap between 22.5 and 26.5. This gap right here. Okay? Because that's the water before and water after. So this is clean 4. Can someone tell me what this Q comes out to be? 399?
Yeah.
So this is what you're telling me?
Yeah.
Okay, and you can keep it as 399 too if you want on your calculator. It doesn't really matter. Okay, so this is the energy that the water gained. This must be equal to the energy that the metal lost, so you can plug it in. So that means that, actually I'll sort of shorten this here a little bit. That means that 1640.40 is equal to 57.05 times C times 73.5. Okay? So let's simplify this. Let's see here, 1640.40 What's 57.05 times 73.5? What does that come out to be?
4,193.175.
175, I'll just call it 0.18 times C. What do I need to do to both sides to get my C? Correctamundo. Boom, boom. I'm just really writing this whole thing out. It's a little obnoxious, but I want to make sure no one has any confusion on exactly what I'm doing every step of the way. This will cancel out with this. So what does that come out to be? 1640.40 divided by 4193.18 is what? Yes, CC. 0.39. Somebody give me some units.
Joules per gram Celsius.
Joules per gram Celsius. Comparing that to our heat capacities chart, this must be what? Copper. Exactly right.
How did you get the 4,193.1?
57.05. So if I'm highlighting 57.05 times 73.5 is equal to 4,193.18. Does that make sense?
Yeah.
Yep, it's just a simplification. All right, good question. Glad you asked. So on your quiz, you will be given everything here in blue right there that I have highlighted. And you will be asked to do everything else. Okay? I might ask you for I might ask you for something else, but the skills will be the same. Okay? So you'll have to be able to do a little Q to Q situation. Q loss equals Q gain, that kind of thing. All right, so make sure you're able to do that. I'll give you guys a little bit more practice on that later this period. Now, let's see here. So, you don't have to write this down, but I'm going to come at you guys with a few questions here, okay? The other part of your quiz will be over graphs that look something like this. Let me get a little prettier one here. Okay. Boom, boom, time, temp. And so you might have a graph that looks something like this. Boom, flat, boom, boom. Phase change graph, okay? And there's 5 different sections on it. So you got some A, got some B, some C, some D, and some E. Okay, because you got 3 slopes, A, C, and E. You got 2 flat parts, B and D. Again, this is just, I'm doing some notes on the board. You don't have to write this down. But here are all the different questions, and there are a lot of kinds of questions I could ask you about this, about these different parts. So for A, B, C, D, or E, I could ask you the following. Talk to me about the kinetic energy. What about the spacing? Whew. Spacing. What about the movement? What about the changes? What about the phase? What about the temp? Mr. P, I'm not really sure what you mean by each one of those categories. I'm glad you asked. How about I go for an example for each one? So, for example, I could be like, Ian Ford, talk to me about the kinetic energy of C. What's this kinetic energy? Talk to me. Like, compared to other sections, what will be happening? Talk to me.
Right in the middle.
It's right in the middle.
Yeah.
We're somewhere. We'll have high kinetic energy, low kinetic energy, medium kinetic energy.
Higher.
Higher, okay. Can you tell me what phase of matter we'll be in this section of the graph and C?
Solid? No, liquid.
Correct, we will be in liquid. And what do liquid particles do? What are they doing?
Sliding around.
You're kind of sliding around. They're not sitting still, going nowhere, but they're not like freaking out. So their kinetic energy will be kind of like a medium kinetic energy. Does that kind of make sense? Okay? Hey, Andrew, talk to me about the spacing happening in the particles at E. Are they really close? Are they super far apart? Kind of medium? What's going on?
They're going to be pretty close because it's in a solid.
Yep, it's a solid, so they'll be very close. Very good. How will they be moving, Andrew?
They'll just kind of be like vibrating.
Yep, they'll be vibrating. They'll be like vibrating, but they won't really be going anywhere. So they'll just kind of be doing this. Okay, my fist is sort of shaking. Not bad, not bad. Colin. Oh, I don't know. That one.
Oh, we're safe.
That's when you know you're safe. So let's see here, Colin. As I go from this point right here to this point right here, can you tell me what kind of change is occurring? Nothing? What do you mean by that? It is staying the same temperature. Okay, so there's no change there. Other Colin. What about what's happening to the substance itself? Is there some sort of change happening? So the temperature's not changing, but something is. The temperature is flattened out. So what must be happening to that substance?
The phase it's in.
Something's happening, changing. It's changing from what phase to what phase?
It's going from that's like a gas to a liquid.
Ooh!
Or condensing, right?
Everything you just said is exactly correct. It was a gas at this point, this very first one. It was a gas right there, and it's changing to a liquid, 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 liquid. That is condensing, condensing, condensing. And the moment you get right there, it's all liquid. And it's called condensing. That was pretty good. You did not seem confident, and then
Yeah.
you nailed it.
Yeah.
Big brain.
Hey, Mr. John Grant, let's say,
Oh,
what if I came at you and was like, oh, by the way, I forgot to label. This is a phase change graph for H2O. My bad, I forgot to tell you that. What temperatures can you label for sure? I didn't give you any temperatures on any numerical temperatures here, but what two temperatures can you label for sure, knowing that this is water?
we're like on B's line.
Uh-huh.
100.
Right here, that would be what?
100.
100.
Brain. Big brain.
And then you go down to D's line.
Okay.
8.0
And when you say 100 and 0, you're talking about?
Celsius, degrees Celsius.
Yeah.
Love it.
Dude, it's like
You
a
sure it's Celsius?
Positive.
He's positive.
Yeah.
That's pretty good. There are a lot of things I could ask you about that. Hey, generally speaking, overall energy must be lost because here at A, we have very high kinetic energy. These particles are freaking out, going all over the place. Here at E, the particles are just close together, they're vibrating, and so they don't have much kinetic energy, so we must have lost some energy, so this would be exothermic. Does that kind of make sense? Okay, great. Now, don't forget, you should also be able to tell me what's happening with this thing's twin brother.
They're twins.
Sure.
That was pretty good.
Oh, yeah. That's pretty good.
All right, not bad. First time I've ever done anything artistically good in my entire life. But anyways, so the shoe were on the other foot, and you have this graph. You should be able to tell me what's happening. So remember, from this one, as you go from liquid to solid, that's freezing. But over in this one, as you go from the solid to the liquid, that would be melting. Okay. Please keep that in mind. Make sure you're thinking about the direction we're going. Take a look at the temperatures, what's happening, etc., etc. Now, there are two things that you will be doing. Number one, for the rest of the period. Number one, okay, you will be working on the next page. Okay, so if you flip one more page after the What's That Metal Lab, you have some review. On that front page of review, it's asking a lot of questions about phase change graphs. On the back page of that, you have two more Q to Q practice problems. The answer key to these Q to Q practice problems will be posted in the Wednesday folder right after school today. Okay, but I do have the answers memorized upstairs, so if you want to check in with me, I can help you out, give you the right direction. So, you'll be working on this worksheet the rest of the period, you two virtual folks, right after you get those participation points. So go ahead and take care of that for me. So hop into the Wednesday folder, get those participation points right now before you forget. Virtual folks, I'm going to check in with you, see if you have any questions.